All right, today we're diving into one of the most ambitious, most elegant, and, let's be honest, most controversial ideas in all of science: string theory.
So let's just start with this one. Kind of beautiful thought. What if everything in our universe, I'm talking electrons, quarks, all the stuff that makes up you, what if it isn't made of tiny little dots? What if instead it's all made of these microscopic vibrating strings of energy?
And that right there, that's the heart of string theory. Think about it like a guitar string, right? You pluck it one way, you get one note. You pluck it another way, you get a different note. The idea here is that these fundamental strings vibrate in different ways, and each vibration, each note, shows up to us as a different particle. An electron is one note, a photon is another. Suddenly, the whole universe, it's like this giant cosmic symphony.
Okay, so here's how we're going to break this all down. First, we'll talk about why this is such an ambitious project. Then we'll get into the huge problem it tries to solve, the quantum gravity problem, and why our current theories just break. After that, we'll see how strings offer a way out. And finally, we'll look at the ultimate unification this all points to.
Right, so this first point is huge. String theory isn't just trying to patch up a small hole in our understanding. No way. It's aiming to be the theory of everything. The idea is to have one single, beautiful framework that explains, well, everything, all of reality from just one set of rules.
And what's the ultimate goal here? It's to do the one thing that has totally stumped physicists for almost a century. Write a single rulebook for the whole universe. A rulebook that brings all the forces of nature, especially gravity, together under one quantum umbrella. And believe me, pulling that off would solve the single biggest headache in modern physics.
So what is this massive problem? Well, you can think of it like this. Modern physics has two superstars, two theories that are unbelievably successful, but they can't stand each other. When they're in their own separate rooms, they work perfectly. But the moment you try to get them to work together, it's a total disaster.
In one corner, you've got Einstein's general relativity. This is the master of the big stuff. Planets, stars, galaxies, you name it. It's beautiful. In the other corner, you have quantum mechanics, the undisputed champ of the tiny, weird world of atoms and particles. The trouble is, these two rulebooks describe the same universe, but their rules are completely incompatible. They don't speak the same language.
And this becomes a huge problem when you look at places where the very big and the very small collide. I'm talking about the craziest places in the universe, like the singularity at the heart of a black hole, or the very first instant of the Big Bang. When you try to use both theories there, you don't just get the wrong answer, you get complete nonsense. The math literally just falls apart.
So let's get a little more specific. What happens when you actually try to mix quantum rules with gravity? In short, total chaos. The mathematical tricks that work so well for all the other forces just completely and utterly fail when it comes to gravity.
Yeah, physicists have a fancy term for this mess. They call it non-renormalizable. But don't let the word scare you. All it really means is that when you try to calculate what gravity's doing at a quantum level, the math just explodes. It spits out infinity as the answer, over and over again. And an infinite probability for something to happen, that's just a physicist's way of saying, our theory is broken right here.
And these kinds of diagrams are how physicists map out those quantum interactions. For most forces, they work. But when you try to sketch out one of these for gravity, the math just runs amok. You end up with these uncontrollable infinities popping up everywhere. And like we said, an infinite answer is no answer at all. It's a giant red flag telling you that your understanding is fundamentally wrong.
Now, you might be wondering, why haven't I noticed gravity breaking down? Well, this isn't happening when you drop your keys. This breakdown occurs at a scale of energy and distance that is just mind-bogglingly extreme. It's called the Planck scale, and it's down at this fundamental level of reality that the quantum weirdness of gravity finally rears its head, and our theories just can't handle it. And when I say extreme, I mean extreme. To get a sense of the energy we're talking about here, it's about a quadrillion times more powerful than what we can generate at the Large Hadron Collider, the biggest machine humanity has ever built. So yeah, we're talking about a frontier of physics that is completely beyond our reach right now.
Okay, so that's the problem. A big one. The math breaks, we get infinities, and our two best theories won't talk to each other. So how do we fix it? How do you tame quantum gravity? This is where string theory walks onto the stage with a solution that is so simple, it's almost cheeky. It says, hey, maybe you're just thinking about particles all wrong.
See, the whole problem with the infinities comes from imagining particles as these perfect zero-dimensional points. If you have 2 points, they can get infinitely close to each other, and that's when the forces between them blow up to infinity. But string theory says, hold on, what if they're not points? What if they're tiny one-dimensional loops, little strings? Suddenly they can't get infinitely close. It essentially smears out the interaction point, and just like that, the infinities vanish. They're tamed.
And this is where the real magic happens. You start with this honestly kind of weird idea that everything is a string, but when you follow the math, something amazing happens. The laws of physics as we know them just pop out of the equations. And get this, one of the ways a string can vibrate looks exactly like a graviton, the particle that carries the force of gravity. You don't have to force gravity into the theory, it's just there naturally. It's a prediction.
Okay, so let's wrap this up. What does this amazing theory promise us? And more importantly, what's the catch? Because as you can probably guess, a solution this elegant doesn't come for free.
So you have to wonder, why have physicists been obsessed with this for decades? Well, it's not just about solving that one quantum gravity problem. It's because the theory seems to have all the right pieces to describe our entire universe. Not only that, but it's given us incredible new ways to think about other parts of physics, and it's even sparked whole new branches of pure mathematics. It's just incredibly fruitful.
Okay, but here it is, the catch. The price of admission to this beautiful theory is that you have to accept some really, really weird stuff. For one, the math only works if the universe has extra dimensions, like 10 or 11 dimensions in total, that are just curled up so small we can't see them. And, this is the big one, for all its mathematical beauty, we have zero, and I mean zero, experimental proof that it's actually true.
And really, that's the bottom line here. For a lot of scientists working on this, the point isn't whether we've proven it right. At least, not yet. The real value of string theory is that it's the only game in town. It is the first, and so far only, complete mathematical framework that lets us even begin to ask these deep questions about quantum gravity and get sensible answers back. It's a powerful tool for thinking about the universe's biggest mysteries.
So I'll leave you with this idea to chew on. If string theory, or something like it, turns out to be right, what does that mean? It means that everything you see, everything you are, the stars, the planets, life itself, it's all just the result of tiny strings playing different notes in a grand cosmic symphony. And maybe, just maybe, the most beautiful parts of that music are still out there, waiting for us to finally learn how to listen.